Hi everyone, this is going to be one of the last lectures. I have two more lectures, this being one of the two. Um, we're going to be looking at spatial and scientific data today, and then after we're done with all of this, then I'm going to just move on to how to give a presentation. I'm not going to cover multidimensional scaling and things like that. I think you have more than enough stuff on your plate. So let me go over some of this stuff, and then we'll move on to actual presentations. So let's actually open this up full size. So what are we going to be talking about? We're going to talk, this is a subset of all visualization work, and it used to be this weird clear distinction between information visualization and scientific visualization. That scientific visualization was firmly entrenched from it came from the graphics community. It was all about how much you can put on the screen at a time. So you're talking about volume rendering of a human brain, and it was very hard to do correctly, and that's the science and the mystery and the research questions were all based around how to put as much on the screen as you possibly could. Like it was difficult. The challenge was actually from the graphic side, not from the human factor side. And then the information visualization community had, we have bar charts, we have pie, things like that. The issue ends up being that and actually what my supervisor came up with as when she finally put her finger on it and everyone went, yeah, that's what the distinction is. When I talk about a scientific visualization, the difference is that although it ends up being 3D a lot of the time, and it ends up being 3D or most of the time because the data itself tells you how things are laid out. It's given the relationship to spatial layout is given. So with a scientific visualization, if like a map or things like that, you can't really move things around. I don't know if you remember or if you actually watch it, the Hannah Fry lecture about the Euler spirals for doing a globe. And although it seems like a great little interesting exercise to do, the fact of the matter is it distorted the entire world, so you couldn't actually use them. You can't really use the map because things are not properly aligned. The country does not look like the country anymore. So with a scientific visualization, I'm sort of corralled or constrained to I have to represent what's actually there. That there is a spatial component, I need to include that spatial component, otherwise I'm losing something very, very important. And that is the key, one of the key pieces of pathfinding, or the key bit of context I need to understand the data. Information visualization traditionally was I get to choose how I visualized it. I could represent it in multiple different ways. That's what we were talking about when we talked about facets of our data and how we can show the data in different ways with different visualizations, and they're all sort of tell the entire story. So that was originally what the difference is. Now the two communities have come together. It's less of a clear distinction. People are very happy about this. Scientific visualizations still need to now have to do user studies, information visualizations. Well, also have to do user studies, but they're worried about graphics. They're sort of converged as a community. But there is something very unique and very special about a scientific visualization. So let's do a couple little of these things in here just to make us really nice and depressed. We're all quarantined away in our houses, so let's actually look at Corona yet again because there's a multitude of visualizations for any given topic I can come up with for this class involving COVID-19. So you can have a look at the Vimos. This Vimo link is just an image of the virus itself, what it actually looks like, or how they would render it to show how it looks, including the little spikes on it. We can look at this is I think this is a CT scan. Then actually they do a visualization on top of that to show where air is going in, the amount of airflow into a particular area where there's constraints, and also for people to figure out where you're actually getting these respiratory problems for COVID-19. This is the kind of thing that people are actually using visualizations for. What's special about a scientific visualization? Because if you hadn't noticed, I sort of need to actually show the lungs. I don't want to, I might be able to do an abstract way of doing it, but I sort of want to show the lungs so people can actually figure out where the problem it lies. That means I have a whole lot of mass three-dimensional tissue that I need to sort of represent at the same time without necessarily, I need to show it as a whole, not just as a one single slice. And that's where the real interesting parts of this research community is. So let's look at this other one. I find this, it's a useful thing, although it helped conceptualize things for me a little bit, and so I like it, but at the same time, I hope you figure out where all the horrible mistakes or all the issues with these particular visualizations are. So here would be the list of visualizations over the years, I think from year zero up and down here to modern day, and the size of the actual blob is the number of people that died from this particular disease, and then they use different colors for the different diseases, and then they have a timeline here. And Tufte would have hated this visualization, right? I mean, look at this thing. We have time, but they made sure that they had some kind of weird three-quarters perspective for no apparent reason. They have to show these big blobs, and the blobs, of course, are they volume? Are they area? Is it the radius? How are they representing these different numbers? So they didn't actually have to use the actual virus itself to represent that data. It's not a very, it does catch your attention, but I would say that there's a lot of lie factor with this particular visualization. I mean, look at the Black Death. That thing should just be, well, we'll see a visualization below this. It should be just eclipsing everything, and yet it looks kind of small comparatively to like Spanish flu, HIV/AIDS. I mean, this is 25 to 35 million people, still going on, of course. 25 to 35 million people. There's no representation of the duration of the disease, because HIV/AIDS takes up a chunk of time in terms of temporal data, versus Spanish flu is 2 years, 50 million people, 2 years. Hong Kong flu is 2 years and 1 million people, right? The Here's COVID-19. It's just starting up, and it's notice I take a little bit of solace in this fact that it actually looks bigger than it's supposed to, but it's only 14.6 thousand. Yeah, only 14.6 thousand deaths. Now, compared to bubonic plague, right? Compared to smallpox. So this is a bit of a better visualization, but again, it's still doing this kind of weird infographics distortion of the data thing. So this is the one people always forget about, the fact that they brought smallpox to the New World and killed the native populace of the New World with smallpox in what I feel it's 1520, but the duration is actually here somewhere. Oh, it's actually just literally 1520, maybe a couple of years after that as well. But it wiped out 90% of the native population in North America. It just sort of it just crushed the communities. I mean, the Spanish could not have conquered the New World in remotely the same level of efficiency any other way. They just dropped a bunch of smallpox, walked away, and the smallpox did all the work for them, essentially. It's a horrible, horrible thing that we don't learn enough about. So 50 million, 56 million people from smallpox. The bubonic plague is 200 million people. Yeah, this 14,000 doesn't seem like that bad of a deal anymore. But that's the reason why you want to try and contain a disease. Here's the Spanish flu, by the way, plague of Justinian and not Spanish flu, and bubonic plague might be the actual same disease. So, which is I find weird. Um, and here we have all the other diseases. These are the modern diseases, right? Except there's swine flu, 200,000. But here are all the other modern plagues. Now that we know how to handle viruses and plagues, things are a little bit better. But it is something to be concerned about and to worry about, because you do not want one of these things. Okay. Um, and in case you're wondering, oh, and there's a nice list of where it all came from, what kind of disease it is, and in case you're wondering how infectious this all is, Ebola is only two. If for every person that's infected, it infects two other people. Influenza is 1.5. COVID-19 is 2.5. SARS is 3.5. Here's some measles, in case you're wondering why people should get their shots. Why do we have vaccinations for the measles? Yeah, that's the reason why we have a vaccination for the measles. Measles, mumps, and rubella, right? It's the Once you get a vaccine, it makes a huge difference in these turnouts because otherwise we get a lot of deaths on our hands. Okay, so I thought it was an interesting article, in case you're wondering, but um, and it's trying to do what would be normally a scientific visualization, showing the virus molecule, but there's actually no reason in that case. The virus molecule itself is not actually conveying the information. And so that's the question. Why, when and why do we need to use 3D? When do we and why do we actually need to visually represent our data correct? Like visually represent something, or can we use some abstraction of it? So we're going to look at spatial fields, how we visually encode things, how we visually encode three-dimensional information. We learned vector fields and tensor fields as well. Um, and so other ways of representing 3D. And these are the two main ways that we do 3D spatial data. We can also just do slices of 2D spatial data, but it's no longer 3D at that time. We are using 2D to represent the 3D. So we'll talk hopefully a bit about this, but we're focusing primarily on three-dimensional data and how to show it in 3D. So here are the things. See, if I'm arranging my spatial data, and if it's given, that's the key about scientific visualizations. Spatial data has a given component. It might be geography, like a map. Well, that's 2D. Uh, or we can have like a spatial field, which we'll look at, and that is one value per cell. That's the key of a spatial scalar field. So if I know what the value is for every single of what's called a voxel, volume pixel, if I have the value at any particular part of your brain, the amount of blood glucose being used at any particular neuron in your brain, for example, I can color it a particular way, or every single bit of every single neuron could be colored a particular way. So for every cell, for every value that I need to show at a time, I can give it a particular color. That's a scalar field. And we can do interesting things with that. So we're going to look at isocontours, which means you color the surface, all things that are the same color, or we can actually just directly draw every single pixel, and now we have to use transparency. Then we're also going to look at vectors and tensor fields, and so this is much like in the map up here. Instead of just coloring the map, before when we were talking about chloropleth maps, right? We colored the map in certain areas. That's similar to a spatial field, right? You color based off of what the value is. A vector or tensor field is like us putting the dots on the map. It is, I'm going to put some kind of glyph, some kind of encoding of information on top of what I'm visualizing, and then try and make sense of it. So we'll have different, like we'll have flow glyphs, which is how sort of lines flowing over something. We can have geometric glyphs, textures, how like we can give a texture by just putting the number of dots in a given area based off of a value, and that sort of gives you this feel for how what the value is essentially. But it also gives you a little bit of extra information as well. Or we can have some global features to the data. So what's special about this is I have lots of data at once. I'm constrained in how it's being presented because I can't really, if I'm showing a brain, I need to show a brain. Now, there are times when I may not want to show a full brain, but oftentimes I actually want to see the actual structure of the brain, right? If I'm showing an airplane wing, I want to show an airplane wing. I can't sort of show this abstract representation of an airplane wing. I'm constrained to the spatial component. The structures themselves may be present, like in an airplane wing, but they may also be partially present. So if I say, find the hippocampus in this brain, the brain is not actually made up of all these distinct, easily identifiable regions. They're all sort of smushy and sort of going together, but they're not exactly. It's not like your heart compared to your lungs, although, again, that still gets a bit smushy, right? Oftentimes I'll have things where the distinction between this and this is not obvious, or it's not really slapping the. If you took a random person off the street, showed them this after they got sick and threw up, if you show some random person off the street what the brain looks like, they wouldn't necessarily be able to identify distinct regions. The regions are there, but they're not. But it takes a trained eye to find it. So as you might imagine, because there's some sort of figuratively or literally bleed over between the different regions, that's what the that's where we have a little bit of unknown in there. It's not they're not clearly differentiated. And then because we're dealing with 3D, we have occlusion and shading issues. I can't just use, lightness and saturation and stuff like that, the things we were using before with color on 3D, because the lighting actually means something. It tells you where things are or the shape of things. You use lighting for that. And so you can't just sort of only use saturation or only use uh, lightness of a color anymore. So that's where 3D, we use rainbow colors still to this day, maybe not correctly, but still to this day when you're talking about 3D visualizations, because the different hues sort of people expect to see different hues. It sort of makes a bit more sense in that application. So let's quickly look at spatial fields. So this is one value per cell. That's a spatial field. A tensor field, sorry, did I have only spatial fields? Okay. A tensor field is a whole bunch of values per cell. So I can trying to represent a whole bunch of values per cell at one time. And a vector field is, so we have a vector, if you remember your linear algebra, I have directionality and I have magnitude, right? A tensor field is directionality, magnitude, and a whole slew of other data at once. So I take one particular area, well, we can call a cell, one particular area, and instead of just coloring it one color, I make some kind of glyph that encapsulates a whole lot of stuff. This is very similar to when we were looking at Chernoff faces and other glyphs, where we had a whole lot of data per dot or per little shape that we were drawing, and we drew a whole bunch of shapes. So that would be that's a tensor field. So here's what a scale. If here are my scalar values, here's my values. I could just show numbers, but that's not that effective. But I could show the numbers themselves. Maybe I should color this section here one color, and this section here. We'll squiggle it up and squiggle it up, right? One other color. I can just do a bunch of different colors, but every single cell represented a different way. Versus here's my vector field. I have a vector for each of these cells. I put down an arrow. The length and the direction of that arrow represents something else. So I only represent one number. That might be just the magnitude, and the directionality of it's completely missing. A vector field allows me to represent a bunch of data all at once by just overlaying these arrows on top of it. So I can represent just magnitude with scalar values. I can do magnitude and direction with a vector. I can go even further than that later on if I need to. So with a tensor field. So here would be, my value of 4 and a particular directionality of it. It encodes a lot of information. A tensor field, on the other hand, allows me to do a whole lot more, and it gets a little confusing. So I can do multiple variables with magnitude and direction at the same time. So I could be, you know, there's the directionality based on how it's pointing. It could be directionality based on the angle that the shape is in, how three-dimensional it is. Could also be indicating some other dimension. I could do shading on top of this. I could do different colors. We'll see a bunch of vector fields soon. I don't use vector fields very often. It's not my area of knowledge. So, or it doesn't get used all that often from what I come from. But when you're an expert and you're looking at CT scans all day as a doctor, you probably get very good at reading these things. That's a lot of this is not meant for novice users. This is meant for expert users that can finally make sense of it. And you really need to know your application domain to really be able to explain out what the heck's going on. So just hold on a second. Actually, I want to make sure. I'm getting a little bit paranoid here. I want to make sure I'm actually recording. All right, I am recording. Good, thank you. Okay, just on the off chance. Okay, so let's go back to this. Here could be the neurons in your brain, And you could say different regions of the brain based off of color. So you can color your hypothalamus, or not hypothalamus, your hippocampus, or your corpus callosum, or name some random bunch of Greek letters, Greek words for the different regions of the brain. And we could actually encode the directionality of neurons connecting to it this laterally and versus vertically, and then the length of the neuron itself. Or we could show things like the amount of action potentials in that particular neuron versus the neighboring neurons, or it could be all sorts of other dimensions. By having a giant shape with contours with different dimensions and showing all of them at once. Sure, you're not seeing individual neurons. The point of a tensor field is not to figure out what value this value here. You're not trying to find out what this value here is. You're trying to figure out what the brain looks like, or you're trying to figure out the general sense of all the data. So it might be something like this. Here's a bunch of neurons. I have a particular orientation for everything. I can see the overview of the brain itself, and maybe this is my tensor field, and this is a zoom in of my tensor field. Right? That would be a use case for this. And so I'm still seeing the overview, but when I go into the detail, I can get a sort of sense of how things are connected. I like this one a bit more. Right? Here's the brain. Here's this part of the brain that I'm zoomed in on. You can actually see how the neurons are connecting and what directionality the neurons are connecting in, for example. You can also, I think, probably they're doing the number of action potentials or the amount of activity in that neural cluster for a particular period of time. We can go even one step further. We can have pattern tensor fields, right? So we can have this different patterns on the two different color patterns here, and we can have a tensor field that elongates in different dimensions, and we have different how the overlap is actually working. You can do all sorts of crazy things. I don't actually know that research myself, but we have tensor 1 and tensor 2 at the same time per glyph. We are essentially representing two tensors at the same time with one glyph. And people can make sense of it. I've never tried, I've never worked with this sort of thing, but people do actually make sense of it. It is essentially packing in as much information as you can per glyph or per tensor. The issue with this is people were coming up with these great ideas for how you can show four more pieces of data, but I'm sure many of you have realized the first thing you need to do when you've come up with a glyph like this. What do you need to do? You need to prove that it works, right? You need actual experts using these things and actually making meaningful insight using the data. Because if you're just trying to get all cutesy and show how much you can pack into one glyph, it's not really useful unless people actually can make meaningful insight from the data. And that's one of the reasons why the scientific and information the visualization communities came together and stopped being quite so separate. Because, quite frankly, if you're doing a tensor field, you better prove that it actually works, or at least have some good, solid empirical evidence. All right. So we looked at tensor fields, but we're not going to go hardcore into detail on that because I can't. It's not what it's a very, very specialized subset of the visualization community, much like graph visualizations. And we looked at space. So we looked at scalar fields, and we looked at tensor and vector fields. And the tensor and vector fields are me overlaying or removing the original and overlaying a bunch of glyphs, or overlaying on top of it these vectors, or these icons indicating what the heck, the whole bunch of dimensions of data at once. So here's another bunch of vector field examples. Now I'm going to have to actually pop out of this just to read what the heck the actual take-home part of let me point. So they did actually an experiment in 2001 looking at vector fields and seeing how effective different vector fields are. And so this is a grid vector field, this is a jitter vector field, this is I don't know, I gotta look into it. It's a grid. Oh, what is it? I'll have to look into it. This is a grid. Darn it. Yes. a grid seeded vector field, but there's some other part of it as well. But I'll go over it. And this is what, when we say textures, this is sort of what I meant by a texture, right? You're showing little bits everywhere. You're not showing individual arrows. You're just sort of getting a feel for how everything goes by putting almost continuous bunch of dots in a line, right? Versus I can have a arrow showing directionality in here. The vectors themselves are showing directionality. This ends up being an arrow, but it also has both directionality and the shape of the arrow is actually going to be changing. Turns out, for the most accurate approach for a very specific task, this approach is the best, and these two are pretty end up being pretty accurate as well. So I wanted to read the actual thing here. So arrow grids on a arrow glyphs on a regular grid, arrow glyphs on a jittered grid, triangle wedge. So this is regular. This is, it changes depending on where the, how dense things are. This is triangle wedge glyphs, dense texture base. This is texture based line integral convolution. Sorry, reading, not my finest skill. Image guided streamline seeding. So the image itself is guiding how how the lines are working and how they're streamlined, and then regular grid streamline seeding. So this is the interval which the arrows are drawn is on a regular grid versus guided by the image itself. All this to say, if you're doing anything like a vector field, there are well-known tactics and patterns that you could follow. More importantly, there are different tools for different jobs, just like we had before. This just happens to be for certain tasks, certain kinds of vector fields are more effective than others. It's not just a one size fits all. Perhaps more interesting, these are old ideas. So, and you'll be kind of weirded out maybe because of my lack of knowledge of tensor fields, because this is what I used to do for a living. But this is old, as in, notice who the heck wrote through these drawings, right? Da Vinci's coming up with this stuff, seeing how fluid flows. He's actually have his drawing style to represent fluid flow, right? Using lines just by the fact it's a fluid. It sort of makes sense, but if you're trying to represent how some kind of invisible air, like air or things that you can't actually see but how they're flowing, this is a natural mapping, which is a fluid flow visualization. So here would be an example of a fluid flow visualization, right? I have a sphere, I have the lines hitting it, I get the currents going around that particular sphere. I can draw the lines themselves. I can also, this is a vector field, but this is a fluid flow visualization or a fluid line right here, this blue line. They serve different purposes. One is showing how the thing curves around it, but the other one is just the overall flow of things. And if you want a ton of great examples, you can go DFD 2019 as well as another great bunch of visualizations. There are a lot of people doing a lot of research in how you visually represent all of these things. So I strongly suggest take a pause, have a look at some of these things and see what you like. They are less about encoding the data and more about visualizing an actual phenomenon, but that is part of what you're looking at. It is the natural phenomenon that you're trying, rather than just reading raw data, it's sort of getting a sense for how the phenomenon is actually working. This is another Michel Bourquin work. So this is arterial blockages and sort of coronary arteries, and you'll know there's a fluid flow here visualization, and we have a vector field down here showing 3D arrows, of course, all along this. We also have an isocontour on the top here as sort of the sheath of the carotid artery. Coronary artery, carotid. And so you'll see there's 3 different types of visualizations in one group. Notice they still use rainbow color mappings for flow lines. Maybe they shouldn't, but they still do. There might be slightly better ways, but this is something that, it's still in use. You can also see So fluid flow examples, you can actually get it from this. Like we have a vector field here, a vector field here, and notice if you animate it itself, you actually get a better sense of what's going on with your visualization than just with the vector field. So I sort of like that sort of thing. And so in this case, we have initial forces, and whether it's a positive or negative initial force, we can color it in different ways, and so you get a sense of what is going on with how the air is flowing around the sphere in this particular example, or liquid of some sort. It's something kind of fluid flowing around the object. Here's where I actually come in. This would be what CD-adapco has done. And now it's surprising how hard it is to find examples of CD-adapco visualizations. I have a couple on LinkedIn when friends of mine from my old work post something new that they did. But I'd like to point out, so here is an airplane with an isocontour coloring the actual plane itself, showing where the wind is actually the amount of wind speed or the amount of friction or heat caused by the wind speed is hitting the plane. We also have uh, contour lines, or we also have fluid lines going off of the wing itself, and so you can actually get a sense of how the air is traveling around the plane and the overall eddies and kind of currents that are coming off the plane. It's not always ideal. So here would be, I think this is going through a particular jet engine. I can't remember exactly what this one is, but here we have a vector field, plus we also have an isocontour for the actual air itself. We're actually coloring the air itself. On top of that, it's going through this one particular barrier, and then you can actually see what's happening with the vector field, but on top of that, how the air, maybe this is air velocity. We have different air velocities based off of this. So this is slower air, and this is faster moving air right here. And this is really fast moving air here and here. We can also do a fluid line from the blade of, I guess it's not a propeller. What's the word I'm looking for? The back of for a boat. Yeah, it's a propeller on a boat. Okay, so here's a propeller. Here's the turbulence being caused by the propeller moving through the water itself. That doesn't quite give you the full picture of what is going on with the water over time. So what you can actually do, and this is where the other part of this whole equation comes in, the thing we're not talking about, but still the semi-elephant in the room, we can take a slice of a three-dimensional space. And if we take a series of slices of three-dimensional spaces, we can actually get a sense of what the system looks like. And if you take the slices of three-dimensional space, like here and here, and on top of that show the three-dimensional flow on top as well, you get the overview, and then you can get some details that you can zoom into. And that's actually the default standard for brains, or for for most medicine, that although you can show the entire body at once, there's something really useful and really important about taking a slice of a particular, of the data or person, depending on how you want to view things, right? You take a slice of the data, and then you can animate in between those different slices. In fact, that's another one of my supervisor, one of her other famous papers. The reason she still gets 3D visualization papers to review is that in the early 2000s, she and her husband did a paper on how people analyze CAT scans of the human brain. At least I'm hoping I'm remembering that right. But so you take a scan of your brain, you go through into a CT scanner, you get a whole bunch of scans of your brain. You essentially get three-dimensional data about your brain, but no one looks at it that way. And so people were trying to do all sorts of ways of doing three-dimensional representations of the brain. And what they found is the best thing to do is take a slice of the brain at some particular point in time, and then use the wheel mouse, literally your wheel mouse, and just allow it to go in and move the wheel mouse forward and back in space. So that if we have, let me see if I can do this. I'm going to use a sphere or semi-sphere, and using the wheel mouse, that plane can move in and out, and people can make sense of the space more effectively than trying to represent all of it all at once. Ideally, you want both. Sometimes you want a slice, and then you want the context, which is the three-dimensional space. Or you might want the flow, and then you need to be able to put two and two together with a two-dimensional image and a contour flow, or and a vector field. And it's this combination of different visualization approaches that are sort of ideal. And so if you want to have a look at this is a bunch of simulations and particle flow dynamics for a company I used to work for. A bit boring in terms of videos, but I think an interesting view of what is actually being done in industry, what engineers are actually using to analyze how their systems work. When they build a bridge, how well does it work? When they actually build a space shuttle, or they build a drone, or they're looking at how heat is dissipating from an engine or from a battery when they're charging a battery, how heat dissipates from it, how if you're molding, you're casting plastic molds, how well does heat dissipate from it, and if you're going to have a problem with your molding process. All of this uses a scientific visualization, and the key is being able to try and figure out how things are changing over time, and also how you know how heat is just. You want to be able to represent things both using either a glyph, contour flows, or isosurfaces. We'll look at some isosurfaces right now. So here's our spatial field thing. We can just represent magnitude. Here's another thing I could do, right? I could just use a color for my scalar field. Well, that's going to make it get a little bit crazy, but it's a good first approach. So every single pixel or every single part, cell, every part of the brain that's a particular has a certain amount of activity, or whatever the unit I'm trying to measure on, what I'm showing on the screen, I can use a particular color to show what's going on with that. Well, I could do one step further though. What if I did this? So an isocontour is I draw an outline around all of these parts. So it might be this. Depends on what my level of granularity. Or maybe it's I choose a subset and do that, right? That's what I have over here. An isocontour is I try and do a contour line around a particular area based on a single threshold value. And this is actually really useful because if I had all these different colors, it's going to look like confetti. It's going to look like, just a whole bunch of different colors. An isosurface or an isocontour is a line outlining an area. An isosurface is all things of the same value are colored one particular way. And you sort of try and make one region all the same color. So here would be an example of an isocontour. Right? You've been using them, or at least if you've gone anywhere, hiking anywhere, you've used this sort of thing. The isocontour is how high this region is. This is all the same height of hill, right? I go one level above, it's all the same height of hill. It tells me where the hill region is. It gives a nice sort of automatic sort of texture to get a feel for the height of a hill. I know if the hill's really, really, really steep, like right here. Well, I have a whole bunch of contour lines, all in rapid succession, meaning it's almost a sheer face or a sheer cliff. If they're separated, it means that it's a gradual incline, right? It gives me a lot of information that I couldn't get otherwise. So isocontours are used everywhere for maps. We can also have isosurfaces, as in everything with that same point gets the same value. And I can color it, I can use shading and stuff like that, but I give the color yellow to everything on the outside surface that are approximately the same. So I get a sense of where the shape of something. Now that's really useful in things like, let me see here. I'm going to go back in a second. Like, here's my heart. I want everything for the heart to be colored a particular way. Or here is a rib. I want everything on that rib to be colored a particular way. Or here is, I can group things based off of either the same value or the same categorization, and it allows me to remove or fade out or ignore certain things, parts of the body that I don't want to look at a time. So an isosurface is really useful if I want the surface of just the heart but not the lungs, or just this part of the brain but not another part, or just this part of the wing that I'm looking at. all parts of the wing that are the same have the same isosurface. Volume rendering, so that is, I want to throw away most of my actual 3D data. I'm going to only show this isosurface to give the sense of what the image looks like. It is the chloropleth map of 3D rendering, right? Everything that's the same gets the same color. Volume rendering, and like an and like a chloropleth map, the size is based off of, it's based off of it could be a categorization or it could just be where it is on the surface. And you use a constant value, so they're all yellow, and then I can use shading and coloring and things like that to actually sort of make it look three-dimensional. Volume rendering, on the other hand, is I'm going to show everything all at once. So instead of trying to have a surface, I just say everything can show through, and we'll use a certain amount of opacity. They'll be semi-transparent pixels, if you will. So every bit of that, knee or whatever I'm looking at is shown, but the further back it is, the further away into the screen it is, the more. So at the back of your brain, if you're looking at the front of your brain, and the pixels at the very, very back of your head are going to be covered up more than the ones at the front. But you allow a certain amount of transparency for all the pixels, and so you get a sense of where everything is, and sort of like this ghost image where stuff at the front still looks at the front, but I can sort of see things at the back. And if I have a whole bunch of stuff that is all red right here, it's going to show through because everything is transparent. So I would like you to have a quick look at this, and this is actually going to be an in-class exercise right now. The Visible Human Project, I actually really should have, I got to double check what the Visible Human Project is actually going to do. If it's still up and running, I forgot to double check that. It was up and running last year. So the Visible Human Project allows you to examine how a human, you can do slices of the human. You can actually look at individual things. You can change how the contouring is actually working. These are the YouTube videos for it. Hopefully we have, there you go, slicedrop.com for medical imaging. And then I would like you to have a look at a healthy human brain. So, Visible Human Project is, you can just watch the videos for it. Slice Drop allows you to actually look at a human brain. So hopefully it's up and running. Yes, there we go. And do I want to look at fibers? And healthy human brain. Let's look at this one. So you have a bunch of different values as well. This would chew up any kind of bandwidth. If you don't have good bandwidth, that's something, a dangerous problem. And we can actually slice and dice. Remember I said you can move things around, you can change things, you can, but you're getting a two-dimensional view, a slice of the brain, but you also have this sort of volumetric view of the brain. We can also see the individual fibers, and we want like fibers of a particular threshold, or maybe I want only really long neurological fibers in here, and the amount of opacity for all the various parts. So this will cover pretty much everything that we've talked about so far. So what I want you guys to do is have a quick look at this, play around with it, see what you think, see what you see, and get a sort of a sense of how things work. So you can look at the 14-year-old healthy male brain, or any one you want, explore different views, move it around, see what you get, play with some options. Look at 3D and 2D options, move things around, see why you'd want 3D versus 2D, or the combination of the two. Okay, and move around the sliders, and you can look at the fibers themselves. And so what I'm going to ask you to do is, I should also put this in here, what I'm going to ask you to do is take a screenshot after you're done, and maybe make some sentences, like write a little mini paragraph about what you explored. It doesn't have to be, Shakespeare, but were you looking? Did you play around with the threshold sliders? Do you play around with the fibers? Did you play around with different 2D and 3D views? Maybe take a couple screenshots, put it on the Google Drive that we have, and that should be it. Okay, so this is a forcing function for you guys essentially. I want you to play with this because I can talk all I want. The act of playing with these visualizations actually is tells you why these tools work and what works and what doesn't work about these tools. So pause the video now, have a look, post something on the drive, and then pick up the video for after that. Okay, hopefully you've all done that. So here we go. So this is what the difference between why I want an isosurface and a volume rendering. What's the difference between the two? Notice there is a distinct reason for having one or the other in a lot of cases. And hopefully you've discovered that with the sliced, what was it called? Slice drop. That sometimes you actually want an isosurface, sometimes you want a volume rendering. A volume rendering is, so it blends transparencies. So things are actually inherently indistinct. You sort of want them to be indistinct. And because sometimes the data itself is not distinct, and putting a fake distinction between things, like if there's no difference between this part of the brain and this part, there's really no benefit to trying to pretend that they are distinct. Versus if I want to separate, if I want to look only at the heart and not the lungs, maybe I want a distinct surface for it. Or if I want to really categorize different things. And so isosurfaces have a real bit, they have a benefit and sometimes they don't. So here's an isosurface, right? I'm looking at turbulence, and this is air flowing over these particular rods, right? It could be, or water, or some kind of fluid flowing over it. Notice it looks like each of these things are distinct. They're little like spaghetti going over this thing. It's not actually realistic for what the actual data looks like or what it's actually doing. It might be useful to know certain parts or where things are going wrong, but if my data is not distinct, I don't want to make it appear to be distinct. I will interpret the data incorrectly if I use the wrong representation. Versus this, do believe this is a rocket engine, and this is the amount of turbulence going off the back or something like that. I don't even know what this thing is anymore, right? But it's not distinct, data. If I have airflow off the back of an engine, I don't want to see a whole bunch of ribbons coming off the back. It should have a level of transparency. I'm trying to get a general sense for everything, and there's not distinct parts of that plume of smoke off the back. It's actually just a whole lot of data, and I want to get the general sense. And so if I want isosurfaces, it's really good for distinct objects. And if I have indistinct objects like a galaxy, but I don't have a distinct, like, oh, this is this part, this is that part, depends on how I want to view things. If I want to talk about distinct star regions, for example, I want an isosurface. If I want to get a general sense of how stars in this particular region are working, despite it being the same data set, I want the blending, I want the transparency. Volume rendering is very good for the overall, and isosurfaces are very good for if you've distinguished the different regions and you want to pay attention to that distinction. And then you can play around with some other things. So this is the Viz 2017 Best Paper Award for Open Space. You can play around with it. It's Surface of the Moon. Here is, I do believe, tsunamis and earthquake information and how it propagates around the world. And this is Inner Life of a Cell, which you can see the interaction between the different parts of the cell, for example. Heck, we're going to talk about how to give a presentation, and this is a pretty darn good presentation. This is a TED Talk on how animations can help scientists test a hypothesis. This is actually what we do in the visualization community. We're providing tools to help people make sense of the data that they get. And this is how animation can be used for that particular purpose, but it can be generalized to visualizations. But also what you do in your degree program, this is a major part of what you might be doing in your degree program, telling stories through data, but also how you communicate those ideas. Okay, so for a take-home lesson, I want to point out that spatial visualizations use position for position information, okay, and occlusion and processing power has always been traditionally a problem, that the airplane wing is blocking the airflow behind it, right? And I can only show so much at a time because you can always show more granularity for that airplane. So I have a processing problem issue. I have three main tools right now, plus I also have two-dimensional slices of the data that I can put in. So I can take a slice of two-dimensional space and just show that, but I also have spatial mappings, so I can so things like this. I also have vectors and tensor glyphs, so like these flow lines. So I can color the individual object, or I can show little, actually this is better for a glyph, right? These vectors, they're not actually existing. This is the air. You could say that's the air itself being drawn. But those glyphs do not actually exist. I'm putting a glyph on top of the data to give a sense of what's going on with the data, giving me more dimensions than just a single color. We have particles, lines, and 2D slices that also are extremely useful for sense making, because what I can't do is show all three dimensions in space all at the same time. So I need ways of sort of suggesting paths or suggesting what's going on in the data. If I'm showing the actual surface itself, an isosurface is for when I want distinct structures like this. I guess this is fuel, this is a bomb, this is a missile, for distinct structures. And I actually want a sort of a volume rendering if sort of things are muddied together, like airflow, where I don't want to distinguish individual components. I want to get a general sense of what the data looks like as a three-dimensional total. Okay, with that, I think we got a whole bunch of extra stuff if you actually want to look at it. Things like powers of 10, or how the supercharger actually works. Even present this is technically a visualization, but I don't like it that much for scientific visualizations. But what we're going to pick up next, and relating to this talk, is how to give an effective presentation. Because although I've talked a lot about visualizations, I think we're reaching about the end of what would be useful for you guys in your degree talking about visualizations. I would love it if at the end of the day, if you can take any visualization someone gives you and just rip in a new one, right? To look at that the plague visualization that I showed earlier and realize where they did things wrong, what design decisions that they made that were not that effective, where the life factor is, where what a better visualization they could do would be, whether if they're showing a 3D visualization, why would they take one approach over another, why would they use an isosurface instead of a volume rendering. These sorts of things I would hope that you'd be more comfortable with critiquing, and when you're generating your own visualizations later, what's going to be effective and what's not. What we're going to be talking about next time is how to communicate that to other people. And that's not the storytelling part, although that we already did a lecture on that. This is how to give a presentation. Because the presentation is coming up, this is a more generalized lecture, not to do with visualizations, but about communicating to other people and what I'm expecting for your final presentations that are coming up a week from now. All right. With that, thank you very much, guys, and I'll talk to you very, very shortly, as in a minute from now.